My name is Nuri. I'll be speaking about some amount of vector search and trying to really answer the question, is vector search right for me? To that end, if you expected slews of code or fancy demos, you're going to be disappointed. But I am going to try to answer the question, is vector search right for me? Roughly speaking, I'm going to give an overview and understanding of what vector search is and what I mean when I say vector search. I'm going to compare vector search to traditional search, so we already have a preconceived idea of what search gave us before vector came onto the scene. So I'm going to do a little compare-contrast there. I'm going to talk about the use of vector search in what's called retrieval augmented generation, RAG, for those of us who learned about that in the last session or otherwise. And I'm going to also talk about applications of vector or vector search as a notion that go beyond and besides RAG, because vector search is not, contrary to some belief, is not just for RAG architectures. It's useful elsewhere. And I'm going to also maybe talk about the layout of the land, vendorism, and some of where could this be found and how can I use it in my ecosystem kind of stuff. All right, so that's what I promised to do, should the gods of technology allow me to. So vector. What is a vector? We'll want to define it. We'll want to talk about, if I had a vector, how does a vector relate to other vectors? How do I deal with it as a data type? And we'll want to talk about efficiency at scale, because as it turns out, those little things about how to compare vectors cost quite a lot of compute time. So vectors. What are vectors? They're multi-dimensional scalars. They're a single buffer. They're an array of multiple elements. What are those elements? Numbers. What kind of numbers? Real numbers. So a vector, this is a representation of a vector in 2D space, and we can imagine that these are all 2D vectors. One element, the first element in the array containing the x value, and the second the y. And we can imagine that if we had space in the vector, in the array for 3 elements, I could describe 3D space, 4 elements, 4D space, and so forth and so on, into unimaginably complex spaces. So when we talk about n space, we're just saying, hey, a vector is of length n, 512, 1024, 384 for all numbers. I don't know why, but there are some embeddings like that. So that's what we're talking about. And vectors, when we look in 2D space, have a direction and an angle. Typically, they start at the origin because you only supply the x and the y, so how come this arrow didn't butt down into the 0, 0? I don't know. I drew it late at night. That's what happens. But we can see that the green and the red are kind of similar-ish, and the blue is kind of longer and pointing elsewhere-ish. So we already have a notion that vectors are not all the same. And we could look at the ends of the vectors, but we'll talk about this a little more. A vector really is a data type, because not only does it contain numbers, those numbers live together. And if they live together, they work together. In other words, we don't want to say, oh, I'm looking at part of a vector. No, there is no part of a vector. If you're just focusing on a snippet of a vector, then that's a smaller vector you're looking at. But it's not the big vector. The vector represents a set of scalars that work together. Now we know how to deal with scalars, right? Numbers, bytes, bits. They're numbers, and we can add a number, we can subtract a number. If we subtract one from the other, we kind of get a distance between them. If we see that they overlay exactly bit by bit, we say, well, they're equal, right? If we subtract them from one another and it's a big number, we say, oh, they're far. If I put them one next to each other, I say, whoa, that's out of order. I can compare them. Well, we want to do the same thing with vectors. We want to be able to take two vectors and treat them as if they're scalar, except they're not. So we had to do some math in order to provide these very operations. And this is where vector math comes in and my mind checks out, because I don't do the math by hand. I defer to the computer and pre-provided functions to do the work for me. So how do I compare an n-dimensional array? How do I compare a two-dimensional array? I have 2 points. I want to know that they're closer or further away. I want to know that one of those vectors is bigger than the other. If I just plotted 2 places, 2 vectors, which one is bigger than the other? How do I sort them? So for vectors, we can consider several questions. Are they the same length, meaning distance from the origin, or from their axis to the point that the number represents? How far along the x, how far along the y, some combination thereof. Are they the same angle? Are they pointing at the same thing? Do they reach the same point? Could they be coming from different origin, but essentially ending at the same point? If they end at the same point in that n-dimensional space, I could consider them somewhat similar or equal. And then if they don't actually point in the same direction or the same exact, what is the distance of them? And I can say what's the endpoint distance, or what's the line distance between the 2 lines, and so forth. So these are various math things, and it turns out that in order to compute that exactly, there's a formula, you know, and you can take the sigma for I to n across all dimensions, and every element compare, do the square, the sum of squares and the square root of and all of that, and add it up together, and you get a result. And that's the math, which we're not going to do today. But the important thing is that there are roughly 3 different ways in which we typically compare vectors. And those turn out to be important when you're doing vector search, because you'll have to tell your index, how are you computing the distance between vectors? The first one is Euclidean. Euclidean is the simplest one of them, because Euclid is ancient, so I guess it's simple. I don't know. But it just compares the ends of the vector, roughly speaking. So it says if the 2 points it ends up at are close, then it's close, and far is far. How did we get there? What path along the way? Doesn't matter. Just that. That seems to be the least popular and least useful one in practice. The second one is comparing angles. That's called cosine similarity. Cosine similarity is massively popular. It has a cousin that's even better, but it is more popular. Not because it's prettier, but because it costs a little less to compute. And if you have vectors that are pre-normalized, namely that all of the numbers there are already shrunk to be in the range of 0 to 1, then cosine similarity produces the exact same measure as dot product, the better cousin that I'm going to have on the next slide that I haven't mentioned yet, but you already know. That was a joke. Usually people laugh, but okay. I understand. The person before me was very dynamic. I don't compare. I vector compare. Fine. So that's that. That's comparing cosine similarity. And then dot product really is a little more of a combination of the distances along normalization in their own dimension that clumps together. Dot product is better. I had to go to 3rd dimension because it's visualizable, but as a concept, the dot product lets you compare things in the right scale, whereas cosine in there would have gotten lost on just trying to plot a combined angle of all dimensions. Dot product does those dimension by dimension and therefore gives you more accurate normalized measurement. So dot product, the cost of dot product is just computational, that if I do that, it costs a little more to compute. But for all intents and purposes, that is the best you can do to compare. All right. So if I had to do that math, and I already told you that Euclidean is really, really easy, but doesn't give you good results, you're like, I don't want that one. And then you have cosine, and it's like, yeah, that's good for as long as I can, you know, get the accuracy right. Maybe I pre-normalize the vectors. And then you have dot product, which works really well. I mean, eventually, all of the machineries, all vector indexes, whether you're using PG Vector, whether you're using Oracle, whether you're using, you know, MongoDB and Atlas vector search, whether you're using Azure Cosmos DB, all of those indices, or Elastic has a vector index now, all of these indexes are trying to do something. They're trying to cut down the amount of comparisons you're doing in real time. Because that math I showed you, the little sigma with a 1 to n, well, when you have an n-dimensional vector and its n is 1,000, that means for every vector, I have to do mathy stuff 1,000 times for 1,000 elements. That's costly. That's like really going to heat the room with the CPUs. So vector indexes try to lower the number of vector comparisons I'm going to do. Whatever comparison method I choose, it's just trying to lower it. And there we have it. That's what vector indices do. They are arranging all of the vectors we fed them in such a way, index, that I can enter with a vector, my query, and do less comparisons around them. Now, some vector indices, there's also a structured, I forget what the acronym is, maybe somebody can tell me, but there's a disk-based ANN. And the disk-based ANN basically says, well, we'll store similar vectors in the similar location in space in blocks on file, and then when you come in with a query, we'll just go to that one file and read those and just do those. Others do it in memory and all kinds of tree-ish and hierarchical tree fashion, but all of them cut the problem in order to reduce computation. So this is why we're talking about efficiency at scale. When we have a search application, not the, oh, I talked to the chatbot once, but a million concurrent, we want a structure that can do this again and again and again, multiple threads, just burn CPU and give me the answer as quick as possible. It's not physically feasible to just scan all of the records I have, all of the vectors, right? And these vectors are going to contain information. They're made somehow, and we'll talk a little more about that. But those vectors represent your data, right? It's like I took from my ontology, from my documents, from my PDFs, all of the important words for the law firm, and I made index on the important words kind of thing, right? That's what we're trying to do. We're trying to create a search experience where information was encoded into vectors, and then we come in and say, oh, I have a question for my database, and those vectors represent my data, and I'm going to compare my query vector against those pre-stored vectors and tell who's the closest, and that's going to be the most relevant one. That's what we're trying to do. This is why, if some of us may have remember from math, there's this thing called KNN, K nearest neighbors, which is a very precise algorithm. I do the sum of squares, and I find the point that's closer to all the other points in the cluster. Here you see on slide ANN. A stands for approximate. We're willing to lose something, approximate. We're willing to lose some accuracy for the sake of speed and efficiency. Because we're in database land now, we need to answer things quickly. If we want absolute accuracy, we could compute K and N against every vector and get a more precise answer. Turns out A and N, good enough. You lose so much on other things that that little lossy thing is a good sacrifice to have. All right. So a vector index is nothing but a data structure that contains a whole bunch of vectors in such a way that when you come in with a vector, it knows where the nearest ones already is. You don't have to scan them all. And there are some, because we use it in database and stuff like that, that we may say, hey, I indexed a whole bunch of data about my customers. I also want to say a period of time. Well, periods of times are not part of a vector. They're not part of the context. They're just extra filters. So there are also hybrid indices that are capable of pre-filtering from the universe of 1 billion to, say, your 10 million, so that then when you go in with vector search, it's even less work. So that's what hybrid indices are. MongoDB Atlas has one of those things. I don't really know about the ecosystem well enough to tell you which other vendors have it, but it exists. Okay, so I implied that vectors are somewhat superior or give you a better effect or are useful, and I didn't talk about why and what that means. So what is the classic search? The classic search is keyword search, right? It's the old Bayesian formula, taking a keyword and saying that the rank of the search is proportional to the frequency and proportional to the document infrequency. The frequency of my keyword found in the document and the infrequency in all the populations. The more it is on both axes, the better the match is. Even that is too much math. Initially, Google didn't even do that. Initially, Google just counted words. They said, here's a document, take each word. If the term query appeared in this document, yeah, you probably want it, right? Which means that if I was talking about a mouse, I would get Little Mouse in the House books. And if I was talking about mice, it was not clear whether I'm looking for vermin or for pointing devices, because it's just a keyword. It means nothing. It's just a keyword. If there's a hit, great. If not, not. Semantic search is this thing that says, well, wait a minute. When I'm typing in mouse or mice or whatever it is, I'm actually looking for a concept. I have in my mind a semantic meaning around this, and I want the computer to bring back something that is semantically related to my query, beyond just matching words. And it turns out that using vector search for this purpose is superior to trying to do all the tricks we could with traditional keyword search. As an aside, hide my vendor badge that I don't have. Look, traditional search did really well for 15 years. Like really, like Elasticsearch is wonderful. They have a vector search now, but I'm saying just, you know, Solr, Lucene, all of these things. Phenomenal things we did there with fine-tuning, with synonyms, and with stemming, and with, you know, all kinds of pipelines, and with dynamic boosting, and with static boosting. Yes, we made it kind of work, but it still had no idea what we're talking about. No semantic meaning. And vectors really bring us into this area where we're actually understanding what a query is in order to sift through data and bring you the relevant results. So a vector index gives you the idea or the notion that it's performing a semantic search, that it understands your data. With vector indices, we can do image searches. If we can encode images in some way, that then vectorize them, and then we can vectorize our query and then match those and find I'm looking for a herd of cats or a flock of seagulls, the band or a flock of seagulls, it should bring it back. And generically, it's just doing vector similarity in all cases. In traditional indexes, it's keyword-based. If a keyword is present in the query, it will influence documents. And if all keywords are present, roughly speaking, the document is more relevant. And even if your query spells a notion, if if a keyword that appears in a document relates to this notion, it matters none. Only if the query keywords are present in the document in one shape or form. And we can't really use that in images because we type in queries in English and images are pixels. So it wasn't really useful for image searches. And it has limits on similarity because unless the person was generous enough to put in a whole bunch of keywords, it's likely that they missed stuff because the document exact composition was with other words that you just didn't type. So it's more difficult to make it relevant. Here's an example. My query is a fine red wine. And let's say the documents are the text in the text column. So if somebody said a great wine, I can see that, oh, the word wine here and here, yay, yippee. So if I did a token search, traditional, then there's a match, right? How much, this is symbolic, don't try to replicate it at home, but this is just to illustrate that this mentioned wine, so okay, great. And maybe a fine was, somebody took the time to work out that a fine and great are the same in a synonym dictionary. Yeah, go do that for all of English language, right? On your domain maybe, but no, we didn't do that. So it got kind of a lower score. Whereas semantically, a fine red wine and a great wine are pretty close to each other. You get a higher score. 1 is a high score and 0 is a bad score, or further away, right? Second sentence, this aged like fine wine. Well, semantic search should give this a lower ranking. This query was looking for a fine red wine, and this is a sarcastic comment. But token search would say, oh, look at this, it's fine, and it's wine, and it's wine, and it's higher because I have 2 token matches. So this is really trying to drive home the idea of token versus semantic. Semantic, what I mean. Token, mechanical. And finally, the last one here, none of these words appear here. Semantic search should have learned from its training of whoever generated the embedding. We'll talk about this a bit, that this is a good match. And token search has basically no chance unless somebody really encoded this to be some kind of very particular niche wine nomenclature and did synonyms and boosting and all kinds of stuff like that. All right, onwards. Are we good with token, mechanical, semantic, meaning? Yay, all right. Cool. So how do we encode meaning, though? Yeah, great, there's magic, but I need to hire that magician. How does it work? So, roughly speaking, we take documents, which are input streams. They have a bunch of words, right? So I can imagine my whole document is just a sequence of words. And I'm going to take it and break it into chunks. And chunks are going to be kind of tokens. I'm going to tokenize. That's not too far from what we did with traditional search. We always had tokenizers, except there, tokens represented a discrete element from the input. And here, tokens are broken only in order to find the relationship between them. And then we put it into an embedding model. This is where the magic happens or happened already. Embedding models are the things that are able to take my language, my words, my word salad, and convert them into a vector. An embedding model is an AI operation, a machine learning operation. It takes the text, builds a neural network, finds all kinds of, weights and biases to the formulas of the neural network, and as a result, a vector for two similar concepts, both vectors will be close to each other. And a vector generated from an a good embedding model for two dissimilar will end up far apart. So all of the magic really doesn't happen in the vector search or the ANN or anything like that. It happens here. Somebody trained an embedding model to be able to convert your image or your text or your image and text, hybrid models. Somebody took the time and expense necessary to build a machinery that you feed it text one way and it comes out with a vector the other side. I'm not going to talk about how to build those because I don't know. But there are Python libraries for it, and certainly it's a worthwhile endeavor to learn about them for your particular use. There are differences between them. They produce different qualities. I wouldn't say one is universally superior. I would tell you that just working with different embedding models recently, the vectors were such that it was very apparent without having to do too much work that using one for the vector generation and search and another produced very different results in terms of retrieval. So my advice, undocumented here, is try different ones. If you're going to run your data set through an embedding model, try different embedding models for your use case, and you'll be surprised how different they are, even though they're all quality. Yes, sir?
Isn't the embedding model dependent on the model that you're using, you're adding to?
So the question is, isn't the embedding model dependent or related to the model that you're using? I'm assuming the model that you're using means the LLM and the RAG architecture, and the answer is absolutely not. Meaning that the embedding model on its own is based on some linguistics and training and labeling and stuff that somebody went through. But it produces a vector. And all its job in the world, in RAG architecture, that we'll talk about in a minute, is to find documents relevant to the query. But it doesn't answer the query. It just says, I want to map similar concepts to the same dimensional space and further concepts to different places in that same space. That's all it does, for the purpose of that then when I go to take a random concept, I can map it into space and say, hey, what's around there? And it will find similar stuff because it's in the same space area, and further things in space will not appear relevant. That's all it does. It's just pure mechanics. So there's an input stream, that's your data. There's an embedding model, that's somebody built an embedding model and you borrow it or you pay for it or something, and then it generates a fixed length vector. You stick that in a vector index, and now you have a database of vectors. A database of vectors that knows how, when you bring it a query, to find the most relevant vector to you. And now we're going to retrieval augmented generation. That could be exploited. If I had a question about stuff that ChatGPT was trained last year, how does it know what happened just yesterday? ChatGPT was trained on open data. How does it know the documents in my private database in my company? Doesn't. So what we're going to do is we're going to do some prompt engineering. We use RAG when we want to do semantic search, meaning I want to find relevance, not keyword matching. When I have proprietary knowledge, whether it's because it's temporal, the LLM was trained long ago, or just private data that LLM never knew about. And we want freshness, meaning we don't want to have to retrain the LLM model, which is very costly. I'm talking tens of millions of dollars. So we don't want to retrain it every time a new document entered our intranet, right? We don't want to have to rebuild the whole LLM model for every query or every day. That's very costly. So with no RAG, what I would have done is a user would have asked the LLM a question. Hey, what internal form should I use to ask for a new chair? Return to office questions, right? And then the LLM would have used, whatever it was trained on generically and say, oh, use IRS 4562, depreciation of fixed assets, right? What else does it know? It doesn't know about the procedure at Marklar Corporation. How would it know? So with RAG, what we do, it's a little more complex. The user first asks a question and creates an embedding. So it asks the same question, what internal form should I use for the thing? And it asks the embedding model, not the LLM. Ask the embedding model, hey, given this text, give me an embedding. Remember, previously, I took all documents, all forms in my company, and created embedding for them. So now, I want them to meet. So I take that embedding, that query embedding, the transformation of my words into a vector, and then I take that vector it gave me, and I go to the vector index. And I say, hey, I have this vector. It's no longer English words, it's a vector from the same space, the same very space of all my documents. And I give it to the vector index, and it tells me, here are the things closest to it. So now I have a bunch of documents. How many do I want? I don't know, 1, 2, 3, 10. Your application will determine. But I take that, and I say, ooh, I found some documents that talk about that from my own company. And now I give that to the LLM. And I take the original text that the user asked. What form should I use for? And I say, hey, the user asked, what form should I use? And I found these documents that seem relevant, A, B, C, D, content. And I tell the LLM, hey, can you summarize it for me, please? So I do prompt engineering. Really, RAG is prompt engineering pipeline. It takes a user query, goes to a side tour to vectorize it, go to the vector search, find relevant documents, and says, given those documents and the user query, please answer me. LLMs are good at that. They can read stuff, summarize it, seem to be reasoning with it, but now it's grounded. It has context that is fresh from my internal database. So it gives me relevant results. Are we good with this so far? Good. Yes, sir. Text. Right. So I'm not sure what the question is, but I'm going to repeat what I understood from what you said. There is a fine line invisible in this picture between the embedding model and the LLM. Two different animals altogether. This might be ADA-04, the embedding model, and this might be ChatGPT or Anthropic or, I don't know, Cohere, I don't care. But those are LLM models. What do LLM models do? They read text and they give you completions. Internally, if they had vectors within them, I don't know about it, and it's not what this talk is about. I'm assuming this LLM, I consider it my intern that knows English, but has not gone to any other class in the world. Doesn't understand anything except for how to put words together. Not only hasn't it understood anything about the world, it puts words together according to reading all books in the world and just saying, you know what? I saw that this word, world, follows hello in most cases. So if you told me hello and it's go, world, that's all it does, really. Embedding models are different. Embedding models are saying, I learned all the text in the world, and it looks to me like this sentence and these sentence are kind of similar, so I'm going to put them in the same spot in n-dimensional space. And therefore, I can ask a vector index, I can compare indices and say, are these related semantically or far away semantically? So it only answers distance questions. Does that answer things? Okay. One more? Yeah.
For example, if the embedded vector is a picture of the process, how you apply it into the company, then this picture is embedded into a vector. But when you query, you're asking the query's text. They're totally different data types. And then when you embed it again to ask the question, how can they interact since they're different?
So if I understand the question is, hey, if you're asking a question in English and there's an embedding of a picture of a cat, how does it fit together? How does it work? So it turns out to do this kind of trick, you need an embedding model that is a hybrid model. Hybrid model are trained on images and text together in such a way that a picture of a cat and the word cat appear in the same place in space, and a picture of a dog and a word dog appear here. Therefore, when I generate a embedding from text from the query, hey, where's Fido? It will go towards the space where the dog is, which includes a picture or a word because it's a concept. Great question. Yes, one more.
It seems like when you did the different ways of thinking of distance between two vectors at the beginning, that for this purpose, you would need to know which one you really want, you would need to know how the embedding model is laying things out, right? So does the embedding model already know what you're going to use for comparison so that it knows where to put things?
I'll try to translate what you asked into my next sentences, and I don't know if I'm going to answer it, but
Okay.
you see this? Is there a dog in here? No. A dog. There's no dog here. There's no cat there. Right. All we know is that given an input cat or an input cat picture, that there will be a vector drawn in 3D space. And a big cat or a lion will also kind of end up in that location in 3D space. We never say, hey, I found you, now draw me a cat. That's not its job. Its job is just to say, I'm storing the whole space, and there's points in which things exist, and if I give you something, it says, what are the vectors that exist around me? Now, those vectors I tie in my database, I just say, hey, this is for document A, or for picture 123, or for something. So when I pick that vector, I can go back to my documents and say, he found that thing. That is related but in space, so that's probably what I was looking for.
But which one you pick that's being close together is going to depend on which of those metrics you use.
Correct. Correct. So if the question is, yeah, so do the embedding models have a notion of I'm an embedding model for cosine versus I'm an embedding model for this? I thought yes, and somebody told me no, and I'm still looking for that answer. If anybody knows mathematically, I'd love to learn. All right, one more, and I'm going to push on, and I'm going to take as many questions as fit until 6 o'clock. Yes? So I think the gentleman before just asked, hey, does it matter that it was using distance functions based on cosine calculation versus dot product or Euclidean? So do I have to use an embedding model, do I have to do distance searching with the same method that the training was done? That was the question, I think. So if I took everything you said as true, how does that answer the question? Do I then have to use the same distancing method of, say, hey, I'm using the same embedding model to compare in the embedding, but am I telling it to do a Euclidean cosine so I think you are still saying, which was my initial intuition, that you need to do vector comparison. The same vector comparison method I use was the one used in training. Because there are embedding models that are called, you know, anthropic V13 underscores cos. So it seems to me intuitively that it would matter, but then somebody told me it doesn't, and I'm just not math strong enough to know. So let's push on. An interesting conversation. Let's maybe carry it forward and just move on to other topics here. And I want to know an answer. So if anybody finds a truth, please let me know. All right, so vector engineering, these are SMEAL, this is RAG, which is glorified prompt engineering. So when somebody says, hey, do you know RAG? Tell them, yes, it's glorified prompt engineering. You take a dumb LLM that doesn't know your stuff, you do vector search to find stuff you know, and you tell the LLM, here's what you know, and now answer this. Boom. Whoa. Getting there. But not just text. Embedding can create it for non-textual data. I can create it for images, and the gentleman in the previous session talked about that for a bit. I can create it for sound. I can take sound waves and convert them. And one interesting application I saw was they're taking recordings of engines that are humming well and engines that are not. And by doing that, they were able to see if somebody's starting to hum not, record the engine right now, look at the database and say, oh, you have a loose piston number 3. That's nice, right? I don't have to go to LLM. Vector indices are useful on their own. If I can encode the data and I have more than one dimension, vector might be for you. If I am operating an online dating site and I have various factors, maybe age, maybe location, maybe, I don't know, preferences of all kinds, I can take each one as a dimension, find a way to encode it, create a vector, and use vector search. Because will I go out of my way for somebody who's more compatible or a little closer for somebody less compatible? Like, right? I can take binary data of various, opaqueness, which includes operational metrics, which includes random buffers and random snippets of transaction streams that may or may not contain transactional financial data that is fraud. I don't know. If you can create a signature for it, if you can extract elements and encode them in some way and train on that and say, this is a sign of goodness and this is not, or this is similar to others and this is further apart, then you can go crazy, go wild, encode your own thing. Those embedding models for English, yeah, millions of dollars, a lot of research, a lot of manual labeling work. But you probably have in your company or in your project things that you can vectorize. And you can use these same techniques and the already existing infrastructure to encode them and then use them for your relevance.
But the expensive part might be figuring out how to vectorize them.
So the question is the expensive part is to figure out how to vectorize them. Potentially. Maybe your knowledge of the domain or the domain lends itself to it. And, you know, like sound waves, quantization has been known. Fast Fourier transforms, you know, transform frequencies into, yeah, X, Y. I mean, there's all kinds of ways. It's probably been done. The science to put all of this together has come together and gotten into focus, but the math behind it, we're not inventing new math. We're using it. Yeah. I do like this image. I don't know why it's kind of, I want a screensaver like that. I don't know. And then, so we can use vector search outside of the context of RAG, is my main message. And we have that problem even on things that seem mundanely like, oh my God, I need to look through things. So, okay, so let's know what those categories. I want a drop down of age, a drop down of gender, a drop down of this, a preference of whatever. And it's like, you don't have to. If you can find a way to encode it, you might be able to vectorize it and give a much more nuanced, blended response. And hybrid, we talked about images and text together, so hybriding is also possible. This kind of concludes this is kind of how it works and how to reason with it and why vector search and this. So now I'm moving to ecosystem. Where can I find it in the wild? Do I have to use ChromaDB like all the Python methods show, things like that? And the answer is no, by the way. But yes, if you like Chroma and it works for you. So major players, Microsoft. Azure has Azure AI Search. So it's a packaged product you can address or service. Cosmos DB has a vector index in it. So if you're a user of Cosmos, you can throw a index on data in Cosmos and thereby gain operational efficiency for not having to maintain multiple places. And the Azure database for Postgres also supports vector search because Postgres supports vector search and it supports the extension pgvector. Simple enough, right? SQL Server, however, on its own does not have a vector index. It recently gained vector operator. So it recently gained a linguistic vector addressing a vector data type. So you can declare a column of type vector, therefore you could store it there instead of a var binary or var char something. But it didn't understand vectoriness. It couldn't compare two vectors and say, are they far or what is the distance between 0 to 1 or something. Now there is a data type and there's also a function, a SQL function extension that is called, you know, distance, parentheses, vector A, vector B. Therefore, you can do the math there with no efficiency, with no vector efficiency. So SQL Server, getting there, the other options exist. In the NoSQL world, Redis has a vector index, so you can do that. It's nice. It always had an array data type, so that's kind of what you use for a vector representation anyway. But Redis is not a transactional database in my book. So, I don't know. It's a NoSQL. I wouldn't quite call it a database. MongoDB Atlas has Atlas Vector Search. It's hybrid with their textual search and also with extra filters. So for very large scale, like you have a huge data set, that thing rocks. I like using that. Elastic has an index, has a database type, has a search engine data type for your field called dense vector, so it has it built in these days. And Elastic is interesting because traditionally it was a keyword search machinery, and now it has both possibilities. So if that's your data store, yay, you're in luck. Atlas also has text search, very similar to Elastic, so that's also possible there. Sorry, one sec. AWS Document DB, a NoSQL thingy-mabob, has an index, and Pinecone has a vector DB as a service. Pinecone is unique in the fact that it is not exactly cloud resident with a major hypervisor. It's its own thing, so you're always calling out and in of it. But, you know, solid, good implementation, commercial support, all that jazz. In the RDBMS world, Postgres has PG Vector, very popular. There's two flavors, by the way, in there. There is the ANN, which is a more memory fast at runtime thing, but takes longer to build, meaning that when you index, when you add documents into your, or rows into your database, it's more heavy to build up. So if you have fast-changing documents, that costs you something. It also has a disk-based, I forget what the acronym, but the disk-based ANN is very fast to build, but slow to query. So it kind of depends on, are you really changing your data really fast or querying it really fast? You might play with it. Oracle has an in-memory neighbor graph HNSW. HNSW, hierarchical neighborhood small world. No, hierarchical near software wonderful. It's an acronym that I can never pronounce. But HNSW is that thing you want. It's basically a tree structure that takes a vector, says, oh, you look like you're kind of in a category of these four, and within these four, it's like, oh, you're kind of category of this 8 and this 16 and and it drills, and when you get to the bottom leaf of there, you end up with just enough vectors for you to do the actual comparison. So that's the fast way. And then the IVF inverted file, that's the slow to read but fast to build. Oracle also has it as an external file, and Oracle being its Oracle-ness, that they manage it for you. MariaDB has a vector index, so that would be closer to the MySQL world, I guess. And SQL Server, pending, not quite there. By no means is this comprehensive, and if I made a mistake or by now, because this slide is 6 months old, there's more, I'd love to learn about it. So back to the original question, which is vector search right for me? Well, I don't know. I hope you learned enough to make up your own decision. So what should I look at? What should I ask myself to answer the question, is vector search right for me? The first one, foremost, is the effect. Will employing a vector search machinery give me a better result than I can get otherwise? Not just cost, just like, hey, is it giving me what I want? If it's not giving you what you want, don't do it. Can I retrain the model? All things considered, if you're considering, when you're considering RAG implementation, RAG is good when you have the constraints that prevent you from retraining your LLM. If I could take the context, my documents about procurement of a new chair, and train ChatGPT and say, hey, by the way, I also have this, know everything about my company, and now I can just directly ask the LLM, that's better, that's more efficient, probably going to give you better answers than what's called a one-shot approach that RAG is. It's a one-shot because I take my context and my query and submit it at once. It's not a conversation. So that's something you want to look at. It could be that your data addition is slow and retraining or fine-tuning a base model is worth it. So if it's possible, you might want to look at it. Should you use a hybrid index or two indices? So a hybrid index, yay, absolutely. Two indices, like have one for keyword search and one for vector search. Bring the results from both and maybe evaluate which one is better at runtime. Maybe employ both and have two result streams so people can judge and then let the best one win. I don't know. These are kind of UX questions. And also you want to kind of ask yourself how much control you want over this. So I mentioned in the beginning that different embedding models will yield different results. Therefore, you will have to probably evaluate a few. You also want to see, do I have personnel in my team that will take it on and really understand how it works? What do you do when these things don't bring great results? What knobs can you turn? So if you're taking a pre-composed solution from a vendor and there's not a lot of knobs to turn, you're stuck with what it gives you. If there's a lot of knobs to turn but you don't know what they're doing, well, that's just chaos, right? So you want to think about those things as you say, oh, let's adopt this. It's not going to be as smooth sailing as the Jupyter Notebook tells you. It's just not going to work that well. And you're going to have to really think about how do you tell that you've arrived. So model evaluation, basically, saying, hey, I got a result set. Is this good? Did it bring me the relevant documents? How much data cleaning do I need to do before I vectorize my documents? I have a client that has some CRM, and one of the issues is that a lot of the entries in there are mail chains with re. And the question is, do you take the whole thing as a chunk, or you want to break it into chunks, which is meaning unwinding recursively of all of the email chain, deduplicating against messages, because like, hello, 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 you know, it's like just repeating data. So doing that kind of work is not something that's done automatically for you. It's things you'll have to deal with in the real world. Taking a 20,000-foot view, I'm really impressed by how AI, LLM, and things like that kind of ate everybody's R&D lunch. It's been massively popular. I'm kind of glad that chat is like, okay, I don't want to chat with a bot anymore. But RAG is still very relevant, I think, and retrieval of data is still going to be around forever. You have data, you want to access it, which one do you want? That's what retrieval is. So this is great. We're still in very early stage. Those knobs are not quite there and not quite well labeled. So people are trying to figure out, hey, I have some stuff, but I want to promote this product. How do I promote a product in a RAG world? Embedding was already done. There's no like, oh, I'll boost every element in the array by 3 to make it more relevant. If you change the array, you change location in space, it's no longer relevant. So how do you do these things? How do we do static boosting, dynamic boosting? Still a strong question that is not well answered. Limited tuning there. And the expertise skill gap is starting to show, right? We all have FOMO. It's like, oh, Steve discovered how to do all this stuff. Oh my God, I'm falling behind. And Steve's like, I don't know, I just used, you know, the Jupyter notebook that I got as a sample. So I think it's very worth while experimenting with, getting into, playing with a few models of embedding and vector searches, seeing the results come back. It's very good experience, and it's eye-opening. You might never actually put it in production, but understanding how that thing works can make you better in your information retrieval endeavor. I truly believe that. This is my thank you. I think we're kind of out of time. Yeah, 1 minute. Huh? Okay, so there's a couple of minutes for questions. Yes, sir. Oh, I want to mention on the mic, because I can speak loudly, that there's going to be a birds of a feather about search and vector search happening at Salon.
Right around the corner in the Postgres room, and happens at 30 minutes from now. Anybody who's interested in search, vector search, or analytics, I know we'll have to inform you about.
Yeah.
It's only vector search, the semantic search or Lucene query can also be used for semantic search.
I would say only, so semantic search is a marketing term put
Okay.
on top of the mechanics of vector search. I don't think you can say, oh, traditional keyword search is semantic, because it's so mechanically tied to the appearance or non-appearance of a token. So it doesn't have this notion of semantic meaning. It only has a notion of mechanical find, don't find, and add a score of how many of the token actually exactly matched. So it doesn't do a thing like distance. So, so I would say semantic search is the marketing term bolted on top of vector search. Vector search mechanics have to do with vectors. Vectors are produced by embedding models.
Got it. Thank
Yeah.
you.
Question in the back there?
Your email account makes sense for some people, but if you have this with a bunch of documents,
I can barely hear you, sorry. Okay, yeah, that's a good question. It's a very interesting thing to me. So embedding models have a token limit. They like say, okay, I can encode up to this much text. Well, what happens when your PDF or book is much longer? Well, you have to chop it down. But even if you don't, if you have an email, you could say, I'll index the email under the theory that the semantic meaning of the query coming in and searching through the email for, you know, when did Steve talk about, I don't know, naps, that it appears somewhere in the email. But it could be that you want to chunk it still by paragraphs and index each paragraph separately under the theory that this relevance is paragraph bound, which is kind of true most of the time. So a lot of time people take PDFs, and instead of indexing the whole PDF as a unit, they take chunks of it, paragraphs, pages, something, chapter, book, verse, whatever, right? Break it down further under the theory that the query will be about a certain thing. And then when you retrieve it, you can say, ah, it's paragraph 10. Let me also pull paragraph 9 and 11 just to be a little more window context for the LLM, but that's good enough. I don't want to bother you with, you know, it was a best of time and the worst of time and all of that. Like, just tell me when Jean Valjean goes to jail. Sorry, that is a, yeah. Anyway, you get the picture. So chunking is very important. When you're doing chunking, here's a freebie. Add your metadata from the whole document. Meaning that if I have an email from Nuri to Steve about Jean Valjean, blah, 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 then you take that metadata of when the email's from, blah, whatever you decide is important, and you slap it into every paragraph to be indexed. That way, it has relevant in the context of the envelope, plus the very hyper-focused paragraph. And that, to me, in my experiments, that worked the best. Yeah.
there are cases where you build security into the vector database, because the different documents can be accessed by different people, so when you're searching, you apply that context.
So the question is, have you thought of or implemented security into things because different people might access the same data but don't have the same access permissions or security clearance level or something? My answer to you is, I've never done it. My intuition would tell me that what you would do is you would create multiple indices so that I don't accidentally bring context around that could hint at what's in there. So I would create different, I would just spray out the data to different stores that are according to access level, and I wouldn't mix them in any way. A vector itself doesn't embed a security or non-security. I don't think you want that.
Specific to vector though, I mean, I use regular search engines and they will sometimes point me to something and then I click on it and it says, oh, you can't see this.
Well, then they divulge something if they said so. So exactly. So that's why I'm saying I wouldn't want to get into a situation where I was near enough in space to something to come back and divulge the fact that somebody above me can see that I can't, even if I somehow manage to snip it.
But that's the
I would agree. But yeah, I don't have specific implementation experience with that.